if we want to use computer to solve a problem, then we need a program, we need some data, and the data is supplied to the program and it produces the output. This is input is the data supplied to the program, and this is the program, and this program will process this data and then it will produce the output. In case of machine learning, what we do, we take data. This data is a data set, and this data set is called the a priori knowledge. And from where do we get this a priori knowledge? From collection of information. How do we collect information? Maybe by doing a survey. For example, in this case, how do we get this data set? We have visited 15 children below the age of, say, 10 years. Then we have recorded their age and their weight, and these are the data which is being recorded, and this is called, we have collected the data, and this collection is done with the help of doing some survey, and we get it from the field. That's why the data which we have recorded in the data set is 100% accurate. 100% accurate. That is why this is called the actual value. These are called actual value. In this data set, we have two features. First one is called the age. Second one is called weight. And the age determines the weight. It's not like that weight determines the age. Okay, so age determines the weight, but reverse is not true. Weight, if I know the weight, I'm not supposed to determine his weight. Age, if I have the weight in my hand, then I'm not supposed to determine the age. But what I need to do, I have the age, then based on that I will be recording, or I'll have to determine the weight. So that is why age is called the independent feature. And weight, which is determined with the help of another attribute or another feature, is called dependent feature. This is the data. When we use machine learning, the machine learning has few algorithms. This is derived by scientists. Few of the examples are linear regression, then logistic regression, support vector machine. These are all algorithms that belongs to the machine learning studies or data science studies. And these algorithms are designed to process data sets, given data set. And when we apply these algorithms in any available data set, that is called the process of machine learning. Since it is a computing system, it has input in the form of data set, and it has a program to process the given input, and certainly it will produce some output. That output is called the prediction. and this prediction is the output. Again, when we have output, the quality of output is primary objectives. So here the output is basically what we are doing. We are predicting. Suppose that one day we have received a data point or received the age of a children which is not available in the data set, and that actually the age will come from the real scenario. For example, we got one children with the age 6.2 years. Now this 6.2 is not available in any of the data points in the data set. So if I get this data point, if I get this age, I should have, I will give this age 6.2 this program, 6.2 this program. Then the program or this computer will tell us what would be the expected weight of that children. And this is done based on computed by this program. And that is why if I get any information from this computer model or this machine model, that is called the predicted. This is predicted value, and that predicted value will be given to the end user, and this end user is not aware of what is the model we use. It is the data scientists that need to determine based on the data set which model will be used in the process of prediction. Our objective is to find the best model or best algorithm that fits this data set and can give the best result. We are interested in best result. We have given the data set, and what we can change only algorithms, and these algorithms are called machine models in the words of data scientists. These are called machine learning model. In order to predict the future trend in a given data set, what we do, we design an equation. For example, that equation, actually we design an equation. That equation is dependent on the model that we select. If we select a linear regression model, then we evaluate an equation which is called y equals to mx plus c, which is a straight line. The main purpose of designing this straight line is to draw a line in xy coordinate, taking x as the independent feature. In this case it is age, and in the dependent side we will put it in y-axis, and in this case it is dependent parameter or dependent feature, which is equals to weight in this case. And first of all we divide, in order to draw this diagram or draw this line represented by y equals to mx plus c, we divide the entire data set into two parts. Normally 80% of the data points or 80% data points of the data set is taken as a training data set, as a first component, which is called training data set. If I take 10 out of 10, if I take 80%, then it becomes 8 records. In this case, we have taken 8 data points, and we call this the first part, and that first part is called training data set. From the training data set, we evaluate two things, M and C, using a particular specific formula. M is equals to some equation here. That equation will be comprising the data from the data set X and Y. Then based on that, we also compute C. Finally, once I compute the process, once we compute the process of calculation, we will have an equation y equals to say 1.2 mx plus say 0.91 or something like that. This becomes the equation where we have m equals to 1.2 and c is equals to 0.91. Then I draw this line because I know that if it is c, then this is the intersection point, right? This is the intersection point, or also known as intercept. It is 0.91, and this angle will be tan of theta, and that is determined from m. So it will be look like this. This becomes the y is equals to 1.2x plus 0.91. This is the line. This is the line. Then we can plot now for 1, 2, 3 this age, and then weight, respective weights we can put here. We can put few of the points will be on the line, and few of the points will be above the line, and few of the points will be below the line, but that's okay. Our main objective is to create this straight line, and this straight line is called regression line because we are using linear regression model. And when we use linear regression model, we create the straight line. And then any new point, what we do, suppose that 3, if I want to find out the value, if we want to predict the value for 3, I will go to, this is 1, say this is 2, this is 3, and we'll go up this side, and this point where it will cross, if I come to the x-axis, this y-axis, this value is called the predicted value, y hat. However, we have the point maybe here, here 1, 2, 3, 4, 5, maybe 5. This is 5, and this is exactly matching with the 5.0. If it is so, then we say that there is no error. Similarly, for 3.5, it is 5.5. However, if I put 3.5 here, it will go somewhere here, and this is not exactly 5.5. So actual value is coming as 5.5. However, we have predicted that value as 5.4. So if I deduct this, then it becomes 0.1. That means this is the error. This is the error. This is the error. It means that your model cannot 100% accurately predict the result. It cannot 100% accurately predict the result. That means your model is not very good. In that case, what we will do, we will try another model. In case of linear regression, what next we can do, I mean, we can go for another model. Let us suppose we found that the linear regression model cannot predict the result perfectly. That's why we will go for another regression model, say polynomial regression. However, in this case, in case of polynomial regression, equation will not be y equals to mx plus c. Rather, equation will be somewhat y is equals to a naught plus a1x plus a2x square plus a3x cube, so on so forth. Here x is the value of edge, which is the independent parameter. So if I use this equation, then the line that we draw will be different from the straight line. The new line will be somewhat like this. Now this becomes the new regression line, which is given by y is equals to this equation, say 2, y equals to this equation. Now immediately if I look at the data points and the error, again we will do the same thing. We will compute the error by taking the difference between the actual value and the predicted value. If I find that this is almost equals to 0, then the model is good. We will select that. Otherwise, again, if I find that this error is not 0, but it is nearly, it's very high or something like that, then we need to again modify this equation. Maybe now we will go for some other classification or other regression model. So that way we determine the quality of a model in order to predict the output in the near future. So with that basis, let me go ahead and I wanted to let me discuss about the concept of underfitting, overfitting and balanced fitting, right? Let me go to that. This line y equals to 1.64 x plus 0.94, right? This is the equation and this is the straight line that represents that equation. And what we have seen, these are the points, training data points. We have placed all these training data points. Although we have designed this equation from the data points itself, the training data points itself, still there is a difference between the predicted, this is called a predicted value, this is actual value. This predicted value is almost good, this is also good, but they all have errors, and out of that these are having higher error, and this is acceptable error range. So that's what we are showing here. This value is computed from this equation, applying x here, applying x in this location and putting the value of m and c, and this is called the value which is in predicted, means calculated from this equation, and this is the data which is recorded in from the survey. So this difference is called the error, and we can find that somewhere the error is 0.1, it is good, but however error 1, error 0.9, error 0.8, these are not considered as a acceptable, not acceptable. This is not considered as an acceptable error, rather it is considered this error is not acceptable. So what we do, we can recompute the value of m and c again. We can recompute that. Since we found that this m and c does not fit the line properly, so we can recompute the value of m and c taking different set of training data set. For example, we will take 10 data points, but however in this case we will not consider this, we will include few more. Instead of 1.5 I will take 1.6, instead of 2.0 I will take 2.1, that way. So same 10 data points will be considered, but again 10 data points will be considered, however this time the data points will be different. Taking different data points, we will again calculate m and c, and we will form the equation y equals to mx plus c. Then we will recompute this error. Now if the new error is smaller, this is new error is smaller than the previous error, then we'll take the new new values of m and c, and we will form the equation again. Again, we can go one step ahead. We'll recompute this new error or new values of m and c, considering different set of training data from the same data set, and again we will try to compute. If the error, newly computed error, is decreasing, then we will continue the process. If all of a sudden it starts increasing, then we will take it as a optimum value. And at the point where error is minimized or error is minimum, and those values of m and c will be considered as a final value of this equation, final value to be used in this equation. This way we can have different straight lines. Second straight line may be this, third straight line may be this, like this, and the best straight line, which is called best fit line, will be considered for final computation or final model design. Okay, after several iterations or after several computation of m and c with different set of training data points, we found that this straight line does not meet our requirement. Then what we can do, we can go for this kind of polynomial regression algorithm. We can go for this polynomial line. This polynomial line will be computed as y equals to a0 plus a1 x plus a2 x square plus a3 x cube, and so on and so forth. And it depends upon the quality or the shape of the polynomial line that we want, and based on that we will decide how many times these values will be included, what is the maximum power of this x that will be included in the equation. We will notice that all the points are touched, or the line is touching all the points, perfectly touching all the points. This is called exact fit. At this point it is called exact fit. This line touches all the points from the training data set. Now in this case, this training error is 0. Training error is equals to 0, because this line touches all the points available in the training data set. Now next phase is to test our model. But whenever we'll apply these test values here, then we can say, we will see when we apply these test values in this line, we'll see that this test value or the test error is not necessarily 0. It is not 0. Instead of that, it is very high. Maybe it is 10 or maybe it is 20. It means that although we have designed a model which gives training error 0, however the test error is high. If this model produces training error approximately 0 or training error 0 for different training data set, however the testing error is very high. Okay, if it happens, then we call it, this model is overfit model. On the other hand, when we have a model, very simple model, where both training error and testing error both are high, then this is called underfitting model or underfit model. But our objective is to find a model which is not underfit nor it is overfit. So it should be in between, in the sense that training error is also not equals to 0, however it is acceptable, and testing error or test error is also not equals to 0. However, it is acceptable, maybe in the range of 5. For example, 5, this is 6, that's okay. And this is called a balanced fit model, and we should always go for balanced fit model. We have a model like y is equals to a0 plus a1x plus a2 x squared plus a3 x cube, like this. This is an equation derived from the training data set, and here x is called the independent feature, and this independent feature we have added to the equation number of times with different powers of its values. Okay. So as a result, what we will get, we will not get a straight line, rather we will get a line of like this. And this kind of models are called a complex model. Based on the power of the independent feature added in the equation, we'll have different shape of the line, and this line we expect that it will touch all possible points of the training data set. Suppose that we have selected a set 1 from the same data set as training data set, and we have selected another set S2 that is also used as training data set, and we have used one more, then that one is also used as training data set. Apart from that, we have similarly the testing data set separately, maybe say S1 hyphen F1 S1 dash or S1 prime. So what we can do, we can design the model, or we can design the equation using the first set. Then we found out that the training error is 0. Also, we have taken another training set from the same data set, and we found that then also training error is equals to 0. And if we consider the third one, then also the training error is 0. It means that with respect to the training data set, the machine model performs 100% correctly, accurate. So this is because the training error is 0. But whenever we apply the testing data set in the same model, we found that the testing error is very high, very high. If it happens, then it is said that the model is of high variance, right? Normally the complex model, it designs the model with multiple independent variables or using the multiple powers of the same independent variable. Y can also be created as y is equals to a0 plus a1 x1 plus a2 x2 plus a3 x3. This is another form of the complex equation for any regression model. Here x1, x2 and x3 are 3 different independent parameters or independent features in the dataset, and this becomes a complex model that is called mostly the polynomial regression model. So whatever the model, we are not bothered about the model, but we are concerned about the training error. And if we apply a set of training data S1 to the model and we get the training error 0, we apply another set of the training data to the model and then also we get the training error 0. We apply the another one, then also we get the training error 0. However, in all the models, whenever we apply the testing data set, we get a very high error. And if it happens, if a complex model or if a model generates highly varying test error for different training data sets, then the model is said to be of high variance, right? And another concern, another view of the model, if the model is simple, then mostly it generates very high training error, and also it produces high testing error. If both training and the testing errors are high, then this model is called the underfit model. So however, if a simple model generates high training error, then the model is said to be have bias, right? That is, a model is said to be biased if it produces a high training error, right? If it produces high training error, then the model is called biased model. And we do not want any model to be biased, and we want any model to be of high variance. So in between, we need a model which is acceptable for a given problem.